Hey, Shyam. Hey, how are you?
Hey, Gaurav. I'm doing good. How are you?
Okay, thanks. So it's your presentation today, right?
Yeah, I think I almost forgot, and then I remembered Thanksgiving break blurred some memories. But this is a presentation I've given many times, so no issue.
Yeah, I mean, this is something you can do in your sleep, right?
That's probably true. Not a good thing, but probably true.
Nice. And there's Jack. Hey, Jack.
Eject.
Hey,
Know that Pankaj sent me a reminder email, so he might be joining.
I just pinged him. Uh, Let me see if we hear back. Otherwise, I think you should still be able to present, right, Shyam?
Yeah.
Now,
I mean,
try the screen share that you intend to present.
okay, I can do that. So this is let me swap my setting. This is a slide that have, I mean, a presentation that I've given at STC, which is the SNEAR Developer Conference before. And um, I think that was one of the things that we discussed a meeting a couple of weeks back. So I'll certainly go through it. Feel free to stop me at any place if you have a question. Um, I think before we get into the internals of SDXI, it's good to at least set base on some of the use cases that it has envisioned and what it has in mind. And this slide deck goes through that. Another version of this is available in YouTube, but in this format, you're able to ask me your questions real time. So I think that's one of the good things here. So I think some of the accelerator usage models that STXI is trying to solve uh, are discussed in the next few slides. So the first one is about how do you offload memcopy? And a lot of times, the simplest of offload operations is basically telling somebody else to do your copies so that you can focus as an application or a user on more interesting things because application copies end up using a lot of compute cycles. And the use case for SDXI is to offload a lot of these DMA copies, which may end up consuming a lot of your CPU cycles. And in many cases, it's the chargeable CPU cycles that your application is charging you for. The
I
next
just
use
wanted
case,
to ask you if it's okay to
yeah,
take I mean, you want to take questions on the go or hold back?
either way is fine. I can do it.
Sure thing. Thanks. Continue.
Yeah. Okay. All right. So the next use case is the persistent memory usage model, which is kind of like uh, if you just wanted to make the data persist from volatile memory to persistent memory, uh, sure, you could use CPU cycles because it's really memory pointers that you are using a memcopy for. But now you could just use an offload data move interface that says, okay, I'm moving this data from volatile memory to persistent memory as long as it is able to address both kinds of memory. And you can retrieve it back into volatile memory as well. The next use case is kind of like a virtualized data movement use case where your actual application is virtualized and you may not have one but multiple applications. They're all in different address spaces, and you need an accelerator interface that can actually move the data even if the application is virtualized, which means that the accelerator needs to be able to understand user virtual addresses or guest virtual addresses uh, because that's the level of translation you need to be able to reach into buffers in the virtual machine's user space buffers. So an accelerator interface that can reach or do data movement from one VM's address space to the other VM's address space without having to do multiple buffer copies through the hypervisor layers, but still preserving some of the security that you get with virtual machine isolation or, for that matter, containerized isolation is still required, right? And while I'm giving an example of virtualized, this applies to any kind of address space that is isolated from other address spaces. That's the key thing that I wanted to mention here on this use case. The next use case is more related to now that we have different tiers of memory, and now I should just add HBM classes of memory as well. Uh, a lot of times, just moving data between different tiers of memory might cause stalls at the compute level because they're all at different latency tiers. So offloading data movement to an accelerator, which follows a specific standard, gives a lot of goodness in being able to move data between different tiers of memory while not waiting on the data movement to complete just because it's a large blob of memory data that needs to be moved around. So from a bulk data movement point of view, offloading it to an accelerator to be able to move it to different tiers of memory is a use case. This is a memory transformation use case, and the transform here applies to anything. For example, it could be compression, encryption, but anything that involves a memory to memory transform, it can be applied here. Think AI, any kind of matrix transformations as well, right? This is an example of performing compute. Even when you are performing compute, you have data, which is the source data. You're performing some amount of compute, and at a later point, you're storing back the results into some kind of a destination buffer. And so you still need an accelerator interface to perform the data fetch, compute on it for a while, and then submit your results back to a target location. So with some of these use cases in mind, and these are not all of the comprehensive ones that I went through,
Sorry,
the
I had a quick question on the previous one if you were to go back a
uh
slide. So, just this accelerator layer that you have,
mhm.
does it mean it is a device or can it be like, across devices as well?
It can be across devices. The standard allows for you to work with multiple accelerators of as long as they potentially have the common STXI-based memory structures that they use. And now you are part of the same group of accelerators that can perform.
Got it. So
Yeah.
something like, if the devices are PCIe devices, then it can be a PCI peer-to-peer data
Yes, you,
transfer across those in the accelerator layers,
that,
right?
that's
Okay,
correct.
thanks.
And even when we're talking about memory, we're not really just talking about DRAM, host CPU based memory. It could be memory in wherever I mean, as long as you can address the memory, you should be able to use this interface. So if it is not addressable, that's when it becomes a little bit challenging. Like if it's private memory and you can't address it.
So Sham, what we were just discussing a little while ago. So as I ingest, so for me, you say memory. For me, it just turns out to be data. So
Yes,
as I ingest, I can actually transform. So if I bring in from storage, I can transform into whatever is my compute domain in a format that it's agreeable for me to compute on in terms of that. So now this allows me to use your element. It's a transformation engine where I'm actually ingesting data into a specific node, and then as I egress, I can transform back to whatever is appropriate then.
that's correct. That's correct.
Can I then provide something like an ontology, which becomes a map for the transformation as well?
Yeah, that is a I guess at a level you could define that between the user and the engine that you want to have a protocol on how do you want to build it. So at the lowest level, at the dumbest level, this is really just a data mover. But if you build it in layers, you can describe operations that say, I'm going to send you the data in this format. Or you can tell the accelerator that I'm sending you this in this format, but I want you to transform it and then send it back to me in this format. Or I'm going to send you in this format. You can go compute on it. Once you're done with whatever you're doing, send it back to me in this format. All of those are acceptable forms of communicating with an accelerator. It's just that all of those are stuff that needs to be defined within that framework.
Okay, thanks. That works.
Daniel, you had a hand raised.
Yeah, I was just wondering, so what is the story then for an accelerator or device with private memory? Since you mentioned that everything has to be addressable, I'm just curious what kinds of things you can expose from an accelerator that has some private non-exposed memory.
So that's a different scenario. Well, I think what I'm describing here is the source and the desk buffers that the accelerators are working with are the ones that the accelerator needs to be able to address for it to be able to fetch and you know yeah store back the data too, right? Uh, if these buffers are not addressable to the accelerator, then we can't work with it. So that's the only limitation I was talking about.
I see. I see. I misunderstood, I guess. I thought you were saying that the application needed to be able to address them.
Yeah, no.
Okay.
Yeah. There are cases where, like, I think this is because Gaurav asked the question of peer-to-peer. There are devices which have private memory, right? If you were to do peer-to-peer, let's say this memory was in a peer device and this memory was, say, local, and then the memory in the peer device were private to it, and the accelerator can't address it, then we can't really do the data move, right? So that's the only challenge.
Gotcha. Thanks.
So with some of these kind of tenets in mind, we or use cases in mind, we kind of started this standard in SNIA, and it's been the working group has been meeting for more than 4 years now, and it's an extensible standard. It's also kind of meant to be forward compatible, but the key thing that this group will find it interesting is it's independent of the IO interconnect technology. So the data movement that you are doing could be over a PCIe bus, it could be over a CXL bus, it could be using Ethernet fabrics or other fabrics as well, or any of the new fabrics that are coming through. Um, and I joke usually that it could be pigeons as well, right? And that's why the standard is not specifying what kind of interconnect you should use. It just standardizes the structures that you need to describe to tell the accelerator, I want you to move this data. The data exists here. The data needs to be sent over here. You need to perform these type of transformations on this, and where am I expecting my results back? All of those are part of the standard, and a few more things to make sure that this is scalable, virtualizable, all that stuff, right? And it's extensible enough that now you can keep on building different kinds of operations that you keep sending to the accelerator. But at a software level, you can use simple APIs to describe what you want to do. And it's also meant to be ISA independent. That means the accelerator is not going to be based on a specific CPU instruction. It's not going to be based on where it's implemented. It could be implemented on a CPU. It could be implemented on a GPU, FPGA, IO device, wherever you want it to, right? And it is also a standard that is meant to work with memory in wherever it can be. And the application will have a direct access to the interface. That means you will cut down a lot of the software layers that exist today for being able to, describe work to an IO device or an engine or anything of that sort. So that's where some of the benefits of this interface come through. There is also, there is a kernel driver, a class mode driver that is being implemented for Linux, and other operating systems are building towards it. But there's also a library that is being written so that user space applications can directly use this interface. They just need to get a context set up using the library, and once the context is set up, you're now directly talking to the accelerator interface. This is kind of just a build out of a very simplistic model of how an SDXI implementation could look like. And on the left, you start with an SDXI function. I very specifically called it just a function. If you were implementing it as a PCIe accelerator device, this would be an SDXI PCIe function. If you were implementing it as an CXL device, it could be a CXL function. If you were implementing, let's say, as an ACPI device, then it's just an ACPI device function with its own MMIO space. So there are also folks that say, I would want to implement this, and I will just implement this in firmware or software. Then you are a function that takes in all these descriptors and structures that we are defining and implementing it purely in software. Maybe you have a lot of cores that you can spend just to be able to do these type of data moves. The standard doesn't care. The key thing is to know that there is a construct called an SDXI function, and there are some sort of MMIO resources that are expected to be implemented here. These MMIO resources can be programmed to point to what we call context tables. And in these context tables, we describe all the control and state information about what state those contexts are. So if you realize, this is important from a point of view of when we talk about accelerators, we also need to know what state the accelerator is, and they all have to be architected. For example, if you wanted to stop the context and move the job from one context to another context, we need to be able to pause or stop the context in an architected way and then move it to some other accelerator. And that gives us the ability to move jobs from one host to the other host and so forth. Within the context, you will have something called a descriptor ring, and then some read and write pointers, which are like head and tail pointers. So in a doorbell, that is used to indicate new work. The descriptors describe all the buffers that you want to use for moving the data movement, and the descriptor also points to a completion status block where the completion would be returned by the function. And there is a concept of an A key table, which is basically all the address spaces that this function is allowed to access. So for example, if you had two VMs and you wanted to move one VM to the other VM, each VM would be an address space, and the A key table will have information related to that address space. There is another concept of an R key table, which is basically the receive side control, which is if you had a remote function that wanted to reach into your local address space, and any willy-nilly function cannot access the local resources. So the function has to validate that the remote function is able to access the local resources, and it uses the R key table to be able to do that. This inner shaded region is kind of what describes what a user level application needs to know to just be able to send accelerator work, send the accelerator any kind of work. And so all of these structures can exist in memory within the user space. You don't need any additional privileged software help to be able to work with these structures in memory. The privileged software does have control over all of the other regions. So it can control what address spaces this context is able to use, or all the functions, remote functions that can access the local resources and the state around the context. And the spec is designed in such a way that you can have multiple contexts on a per function basis. And you can also have multiple functions implemented. A lot of these functions could be in the same group, which means that they can access address space to address space data movement within the function group.
Hey, Shyam. Sorry,
Yeah.
I joined late. You are specifically talking about PCI functions here, PCI physical functions here, right?
No, that's what I was explaining in the beginning, that maybe you joined that.
Yeah.
The function, we are basically interconnect independent. But if you were to implement this on a PC as a PCI device, you would implement an SDXI function as a PCI function.
I see.
If you were a CXL device, you will implement it as a CXL function.
Okay.
I was also saying that it's also entirely possible to just implement this with a software structure in a function interface, and back it up with whatever number of compute power you want to have, and still be able to perform. The spec provides an example, PCI device binding. But that's not to say that you cannot implement it. I mean, you can also implement it as an ACPI function if you wanted to.
Okay, thanks. Yeah. Thanks for clarifying. Sorry about asking you about something you already explained.
That's fine. So this is kind of, if you look at it, the inner shaded region, just to repeat if you missed it, right? The inner shaded region is what the user level software needs to know. And the outer shaded region is where the privileged software has control over. So all states are in memory, and we have like a descriptor format that's standardized. And then because the states are in memory, it's sort of very easy to virtualize, because now you don't have any hidden states behind the accelerator implementations that you need to go and look for and find out before you can move the job to some other virtualized host, for instance, right? And we did go ahead and register a class code for PCI-based implementations. So in fact, if you, once you will see pretty soon an SDXI class code driver in the Linux kernel, and that would be for PCI implementations, you would just have one class code driver that would register with an SDXI device and initialize it. And now you should be able to set up contexts from even a user space level with that. That's what the library is helping you with. This is sort of the example of a common format, and this is the common structures. I mean, There are control parameters, like specifically with memory ordering, like I will explain it a few slides later, but there is something called an operation group. You may have different kind of operation groups. There's a body that describes what the actual operation does. We have a bunch of operations that have been described already in 1.0. The completion pointer points to where the completion status block will be written to, and it's a 32-byte region right now. This is a little bit more of an eye chart, but it kind of gives you an idea of how the address spaces are described. Like, for example, if you had an address space, to reach it, you needed a specific function. We call that an S-func, but really you can think about it like a requester ID if it were implemented with PCI. And a password, which is an address space identifier for that address space, and a few other identifiers that I can certainly talk about if required. The RKey is the receiver side control that I was talking about, which also identifies the remote function that is allowed to access the local resources. And the function implementation is required to match these to ensure that only authorized remote functions are able to access the local address resources. So, I mean, this is just an example of how multiple address spaces can move data with each other. So imagine you have a producer in address space B, and that's where the context lives, and the context contains the descriptor ring. And you enqueue a descriptor and then ring the doorbell. That causes the function B to fetch the descriptor. Inside the descriptor, you will have, let's say, two address spaces that you are moving data from. Address space A is the source address space. Address space C is the destination address space. So in the descriptor, you will have a key A and a key C in them. And you use the A key entry. I mean, basically, it's this structure here. With that structure, you know what is your target function that you're going to use to access that address space and the password that you're going to use. You'll also know what RKey index will be used to match this requesting function. And so when you do that, you've got your A key entry. With that, you got your RKey index. You use the RKey index to go into the target address space where you will get your specific RKey table entry. So in that RKey table entry, you will find that this function matches with the requesting function, and that's how you are allowed to use that address space. So now you can read into this address space, and then you can do the same thing on address space C as well. Now you have access to that address space as well. You are doing a DMA read from this side and doing a DMA write into the other side. So this is kind of a convoluted, but still a example of how multiple address space data movement happens with this spec. You can imagine that you can do this with just two address spaces, with both address spaces having producers with each other. You can also do this with a single address space just to be able to do data transformations from source buffer to destination buffer. Okay, so that was the quick whirlwind view of that. But just to kind of give you a little bit more, we are also in 1.1 going towards what we call definable operations group, which means that you can define a lot of the operations in a vendor-defined manner and still get all the benefits of what the framework standardization offers for you. You just need a new UUID for each definable operation that you want to describe. the other things that are kind of interesting is in 1.1, the concept is extending itself to, sorry, let me get this, not just single copy, but multiple copies at the same time, right? Like you can take the data from a single source address space and replicate it to 2 different address spaces. At this time, the group has been, and this is all part of the public review spec that has been put out already. So, you know, at this time, the group has decided that they're going to support this 2 address space copy model because we want to synchronously complete the write to both the address spaces before we communicate the completion back to the producer. In the future, it is possible to define operations where you may have a single source and multiple destinations. It is not necessary that the write succeed to all the destination address spaces. So for that, more work is required to define those kind of operations, but it's still a model that can be possible with the framework. This is more of some additional data integrity features that you could do. Just because you're moving data doesn't mean it hasn't corrupted in flight. So you also need to get additional data integrity markers for yourself, whether it's a CRC-based checksum along with the data, or if you're doing more storage like workloads, then you need some kind of a personal integrity information like PI check, strip, update, those kind of things.
Hey,
I already
Shyam, we have some time, but I want to make sure that, like Daniel, if there is anybody else who had a hard stop at 1:30, otherwise we continue till as long as needs.
Yeah, sorry.
What is the next hard stop for people? Sergey, can you stay till the end of the hour?
Yes.
Okay. Anybody else?
I'm
Okay.
fine. I can say.
Okay. Okay. Let's continue, Shyam.
Okay. So I don't have too much more other than, so this is also along the path of what's cooking in 1.1, which is additional transformation operations as you're moving the data from a source buffer to a destination buffer. And one example you can say is compression, right? And that's kind of model that we are going towards. It's we're trying to fight against time to get it into 1.1, but it might overflow to 1.2. But you can think about compression, encryption, hash, all sorts of operations that you can perform as part of moving the data from a source buffer to a destination buffer is all part of the purview of the charter. Let me see. This is one example certainly that's been added to 1.1, which is all the POSIX style memory ops. Let's say, for example, you wanted to fill a large buffer of memory, or you do some kind of simple POSIX style memory ops with that. And then some additional stuff that has been worked on for 1.1 is we had a big hammer in the form of 2 memory ordering bits, which is one is a sequential bit, which means all writes prior to the writes with previous descriptors had to finish before the write on this descriptor has to be executed. And then another one, which is the sync one, which means all previous descriptor operations have to complete before the next descriptor is going to execute. If you don't have these set, any operation can be launched at any point of time. It's fully parallelizable, right? But even though you have those 2 things, there are additional stuff that you could do, which is, like a read barrier. So you will only read a source data after the write from a previous operation has completed on that same address. So that gives you a read after write style ordering. And you can do other things like valid bit toggling to make sure the descriptor is not launched until it becomes valid and things like that. So these are all in the realm of memory-based ordering that you would need to do if you are a memory-based data mover. And there are certainly more than these that some of the group members have talked about, but that's the path that the group is in trying to add them to the standard. This is more of a point of view kind of discussion. If you have multiple address spaces, you would need some kind of a connection manager to broker these two address spaces to talk with each other. The group has been discussing flows and how the connection manager helps broker connections between two different, let's call it clients in different address spaces that have a function with each other. And it is likely that a connection manager can exist outside the scope of SDXI as well. So you should be able to still be able to move the data between those two address spaces. And the initial information needed for you to create the connection may come from a out-of-band connection manager. This is the CXL view that I have talked about previously, which is, you could have an SDXI device as a PCI function. It could simply use a CXL memory expander as a target for memory. So you could be using it just to move data between CPU attached memory and CXL attached memory, if I could call that. Or you can do something more interesting, which is on the picture on the right, where it's actually a CXL device. So it means it at least has a CXL.io function, but it could also have memory within the device. And so now you are able to move data between CPU attached memory and CXL device attached memory. And if you are doing something more interesting than that, you could also use some of the cache optimizations to help you with the data flow. In addition to all the transformations that you could do because of what the standard offers.
So in this one, if there, many devices have DMA data movers that are getting more sophisticated, and CXL3 is bringing in peer-to-peer, right?
Mm-hmm. Yeah.
So question is, if in this one, it's not clear if the initiator can be on the device side, because we are very interested in using some of these as orchestrators on the host, but then doing device-to-device data movement for the best parallel computing offload. And it looks like that's not contemplated yet.
So when you say peer-to-peer, is the peer-to-peer operation launched by the host, or is it launched independently by the device itself? If it is, then yeah, you can certainly, in both cases, you can do that. I think I may have been just explaining the more general purpose scenario here.
Yeah, I mean, I'm trying to see, there were a couple of questions actually in these last 3 slides. Okay. One was the whole outside connection manager thing, which is, in general, you will have, when you have this kind of memory to memory data movement, you want fairly stable cluster. Okay. You don't want to be doing memory operations in unstable clusters. That's inviting disaster. So presumably there is a membership protocol somewhere. Like, if you go back to the very beginning of RDMA, most memory semantic required an underlying reliable something like RC or RD, which required some sort of strong membership and lids, because things did not move with GIDs in InfiniBand, they moved with lids. And lids were part of, some cluster fabric manager having come through, very tight membership being maintained, etc. Okay, or else things will not work. So the fast path in these data movers assumes that there is a stable membership layer underneath for the cluster. And I was wondering, if these, as you think about this heterogeneous world with kind of CPUs and GPUs as one set of capabilities, host-like, and CXL devices with peer-to-peer capability as another type. How do you kind of have interfaces for that membership so that you could exercise initiation from device to another device?
Yeah. So the connection manager construct, and that's where, the reason you don't see a very opinionated protocol definition put out by the group out here right now is because precisely for those reasons that your clients to the accelerator interface could exist in different environments. And so initial proposals that had come out were to have the connection manager in a privileged software layer, maybe in a hypervisor, and that quickly didn't go through because we have use cases like you're describing, right, where you could have producers in devices, you could have producers in other compute devices than a traditional host compute device, right? And so the connection manager is required to democratize all these different producers that may exist for doing the data movement operations and the transformation operations, but they all need to be part of the membership group, like what you're talking about, right? And so they all have the needs to broker a connection or ask the connection manager for it. So that's why the group is looking at the connection manager is a logical construct that can exist anywhere, and it has more of it assumes the role of being the privileged manager that controls the brokering of the connections for different producers wherever they may exist. And part of that reason is why it might be something that could be stitched together using an out-of-band layer, potentially using just Ethernet. And we could certainly describe all the common memory structures required to connect from one address space to the other address space and ask a connection manager for certain services and all of that. But that's right now.
So, there can be RDMA data movers and lip fabric and this type of things, right? OFA products as opposed to SNIA products are the dominant software in that area, right?
Yes.
With MPI. So, and then MPI has concept of rank, which serves the purpose that I was asking you about, which is membership, right? Established numbering and all that. Okay.
Yeah.
So question is, when you look at a developer and they're looking at, some things that are very traditionally MPI type like CPUs and GPUs, and then you start to see these device-like things, which are memory nodes. So question is, SDXI, which starts as an IO data mover, moves into memory space, single host generally in origin, now rapidly growing to cover other use cases, versus lip fabric, which starts in the parallel computing world and potentially evolves to meet memory use cases in heterogeneous environments. Where do we create a stable interface that kind of captures the best of the state of the art? So there are a lot of goodness and things you described today. I'm really impressed with the maturity of ideas, because there was not much to contend, because it really is how things sort of work in the real world, mostly in single host settings. And then I could see that, with a little bit of a squinting of eyes, you could see how DPUs could be brought into the picture and sort of fabric elements that are being asked to orchestrate data movements, initially with dumb CXL devices and increasingly smarter, right? you could start to imagine that. Maybe, once you reach the end of your presentation, I don't know if you already have.
Yeah, I just had a few more point of views. That's
Yeah,
all. But
let me pause and give you a chance to talk through.
yeah, no, that was it. I mean, this was just the different set of use cases that we are working through, which is again the storage flow and all of the AI operations that are still memory based, right? I mean, um, it's still a work in progress, right? Because the standards work group is continuing to work on. And I think the point that you are making is absolutely correct, which is that its origins are from a single host, multiple address spaces within a single host. CXL made it possible that even with the same 1.0 spec that we put out together, you could still do host to host as long as the address spaces are shared or pooled for the memory data movement to happen. At the same time, the way it has been designed, you could have an interconnect that is, Ethernet, if you will, right, between the memory on one side to the memory on the other side. For the connection manager aspect, the group is still deciding or thinking about, do we need to invent a new one, or can we actually leverage things like libfabric that you mentioned? That's why
Yeah.
I was saying that it might be that we might describe the design principles of what a connection manager needs to do, and maybe the implementation could be just using a libfabric model.
I mean, our concern, right, just to be very specific, because you guys are covering many angles, we have a specific composable memory systems with computational memory programming as the primary focus in this group, right? So our focus tends to be that there are these devices generally full of memory with some additional functions built in, okay? And largely we are looking at computational oriented functions like being able to offload neural network layers, or being able to offload column or vector operations, or database uh, query plan fragments for columnar relational data. Okay, those are the type of use cases we have looked at in this group. And for that, the farthest we want to reach out and be stable on is things like sorts, shuffles, transposes, where we say a bunch of devices that are connected to each other using CXL want to offload an entire parallel computation from a set of hosts, might be GPUs or CPUs, that were originally going to do that parallel computation if it was not offloaded to as a near memory compute. Okay, so we've been working on an API that allows us to specify that kind of task and take it on from a bunch of devices. Perhaps in the beginning, dumb memory devices supplemented with smart DPUs to kick things off. So on the data mover side, right, if you were doing, take a very simple example like a merge sort, okay? So you will, want to do something like sort the local runs and then merge them by doing all-to-all personalized communication. So we've been thinking that for the most part, what we want to do in terms of working many GPUs or many CPUs working with many devices wants to look like a collective communication operation, which are very mature in libfabric world because they have the algebraically the right structure so that algorithms people know exactly what to do, and most machine learning and database people already know how to use that. So directionally, we were moving in that direction, which is how do we, how do hundreds of thousands of GPUs work with thousands of devices, each holding some shards of data? And so we want to use parallel computing as our starting point. That's just the nature of the applications we are dealing with. And the data movers that we are looking for might be triggered by, like, some MPI level operation at the top, or some collective communication library operation at the top. So something like, all-to-all personalized communication is an example that will start at the top in like NICLX or Intel 1CCL or something. Bunch of hosts looking to move a bunch of data. And then this stuff will need to go in the back. And so we've been trying to think about, like, what will the physical picture look like that we want to program, infrastructure picture. And with the rise of UA-Link, we have been thinking that increasingly things that look like collection of smart switches or DPUs will play a role in how CXL-equipped devices will be programmed from a bunch of UA-Link connected hosts. That the offload would occur at that boundary, roughly speaking. You get the mental picture, Sham, that I'm trying to paint?
Yeah.
So, in the interest of kind of addressing the next generation infrastructure, we are interested in sort of the scales of the system that we are seeing in these AI use cases, and doing a good job on them. And trying to think that if, say at the top, CUDA or Intel 1 API or, ROCm, these are the layers that are consuming the API that we are producing. How do we semantically level this API so that parallelism, memory, and this kind of considerations, 4 considerations that we have identified as the top aspects that we want to cover in our work, that they are covered at a level so that they can be consumed below, say, specific CUDA libraries.
Yeah, so the libstxi layer, that is what any application or any framework above it could use to exercise these APIs that this accelerator interface provides. That's at the runtime level now. I think the libfabric side of it for connection management and brokering different clients to be part of the same membership group, that's a different API for sure. But I think at least from the CUDA layer, if you were, or I would, instead of CUDA, I would say, let's say PyTorch, right? And if you were a Python and you wanted to use libstxi as a library under PyTorch to be able to move and offload your data to an accelerator that will go and perform your shuffle, sort, whatever you were describing, that would be the layer.
We think that's a semantically not viable place, because we think that things like PyTorch have too much to deal with in terms of application, numerics, and so they use a very stylized interface. And what we see people who are hosting a highly portable PyTorch layer on very proprietary infrastructures is that they're developing their own customized collective communication library implementations. And case in point is NICLX at Facebook, Meta. So that is pretty much the accepted state of the situation that we have encountered in practice in data centers. So we are thinking that it has to go below, not above that. Whatever,
right.
Yeah.
Right.
So we are actually thinking that, if there is NICLX, right, just to take an example, and we had the ability to now comprehend heterogeneous infrastructure that is CXL based, okay, where things with memory are primary entities in the nouns and verbs of the API, then data movements, and I'll go back to the primitive operations, even though I realize that SDXI, especially with 1.1, is much more capable language. Let's say move, copy, share, right? So if you want to actually do a transpose of a matrix or sort of a table, you do need to move a lot of data. And it appears that something that is a multi-host data mover would be a really incredibly useful thing to have for like a sort algorithm or a shuffle algorithm within Spark. So we were thinking that we want to present a lower semantic level interface into these libraries that can be simultaneously consumed from many entities that are participating in a parallel operation. And the setup that you showed in SDXI gave me some cause for concern because it was still very single host style setup. And I was wondering, how will things like passage translate into like somebody who is, programming a whole bunch of GPUs connecting to a whole bunch of CXL memory.
Yeah, so that is an example of an address space identifier. Now, let's say you are doing peer-to-peer and you don't need a passage to be able to address another GPU's memory, then you don't need it. You need an address space identifier. And an A key table entry is, it's basically all the identifiers that you need to address an address space. For a VM use case, you need passage, you need requester ID
Yeah,
for functions and all that.
I fully agree with you. I think the VM use case is very well addressed. In fact, I saw very little by way of gaps on the VM use case, incredibly so. It's very good, actually. Yeah.
But I think to your point, for peer-to-peer, let's say if the address space is addressable with just simply pointing you to a memory pointer, and or there are address translators that exist in the path for peer-to-peer, or you need just some kind of an identifier to be added to the spec to be able to address a specific GPU memory, that's totally within the realm of extensions.
Yeah. I think just by way of planning, sort of the next set of discussions and work items, I think that maybe the use case slide that was at the very end of your talk, we should look at that as a starting point for motivating any changes, extensions, or adoption of what we are trying to do here.
Right. Makes sense.
But let me shut up and give other people a chance. Sergey, Jack, Gaurav.
Yeah, no, this has been very good. I'll need to study a bit more closely, but in terms of principles, it follows what we're looking for. And Sham, I wanted to ask you, what's the status in terms of its uptake and software readiness based on whatever exists today?
Yeah, so you would have seen a patch that had been posted for the SDXI kernel mode driver, but you would see a little bit more activity on that for upstream submission soon. So I will share with the group as soon as I get the links for when the patch submissions happen for the Linux kernel upstream driver. So that's for the kernel mode driver that basically initializes any SDXI device and sets it up. For any user space application that needs to get a context for itself, right? You would need a library helper that will provide you a context. You will basically say, give me a context, and it'll set up context and give it to you. That is the libSDXI project, which is what the SNIA work group is working on. I believe we are targeting by Q1 of 25 the release of that library. this is an OS independent library, which means other operating systems can basically use it and do that. There are other proprietary OS drivers which are in the works that I can't talk about, but they are in the works. That's all I can say. What else? Otherwise, an application that has direct access to it once it gets a context for it, so applications can start using it.
Got
As
it.
for other hardware implementations, there have been public demos. I can at least share a picture of one demo. This was a demo that happened in MemCon.
Uh-huh.
Yeah.
This is good. I think, we will do well, Gaurav, to embrace the move, copy, share verbs, and embrace this as one option for setting up memory controls, where a single host operating system that has purview of multiple devices is able to cause data movement among them using this. And I think additional use cases that we need covered will probably require, here, I think Sergey is sharing a link.
Yeah, I just send a link to the data streaming accelerator we have in our CPUs, which looks
so I think
similar.
This is indeed right, the target sort of portable programming of such accelerators is the target of SDXI, as I understand it, right? And what we are trying to do is trying to see if we can extend that to things that live in the fabric and then to things that live in devices, okay? So that's the kind of evolution I see, right? That if you are going to do an offloaded shuffle or shard or collective operation, then you will need devices that look like NVIDIA Sharp. So they have a little bit of element of like reduced protocol. They have some element of data movement that is offloaded from the host, data movement and data combination transformation. So the operations that Shyam is talking about are good ones. I think the compatibility with the situation that we are comprehending requires us to actually systematically enrich the use cases into a progression of things that we would like to talk with Shyam and Sneha about, which we haven't done yet. So what I'm thinking is, rather than keep it a one-way flow where we are constantly telling them, where do you need to go? We should also, given the signs of maturity that SDXI is showing, we should also use it where it is already viable, right? So I'm thinking that for memory, even if it might be across multiple CXL endpoints in a fabric or pool, that is visible from a single operating system image or a hypervisor image. The constructs are there in SDXI to begin working with that memory. And then they are sort of, their idea of address spaces versus libfabric's idea of address spaces across interconnects that really span multiple OS images. That leaves me wanting, and both libfabric and SDXI leave me wanting on computational memory right now. That is independently programmable and multi-host and multi-device computation capable. I don't think these standards are reaching that right now. So question is, how do we evolve them? Which one do we evolve and how, right?
Right. And that could be other places that could get merged as well. And I can't talk about which places those are right now.
Yeah. So let's close today with the idea that in the beginning of the year, either I will take Gaurav's help or maybe Sergey. I know Intel's a little bit difficult place right now, but or Sham, you at Dell, somebody should look to host a small workshop, because we need a workshop to go through these issues. We cannot do this in half-hour, 1-hour meetings.
Agreed.
I think we.
Yep.
So let's pick that up in the Slack channel and do some workshop planning and scoping. And then I think writing up what we have been going through in these meetings will be good, so that we capture the end of the year discussions. So we have only one more meeting left on the 17th in this team. We will do that with the thought on objects. And I think, Sham, I would encourage you to consider that very seriously, because we are thinking that some of the virtual address space related friendliness, we want to rescue it so that execution of STXI operations are not tied to OS contexts, but rather object contexts, so that they can travel wherever the object goes. You have the ability to make data movements. So after Daniel talks on 17th, we will want to begin some of those discussions, but I want to postpone that discussion until the 17th, okay? Which is once we know what memory objects are or XPI data set objects are, and we already understood what STXI scope and context and operations are, how do we sort of take the best of all places, libfabric, some of these ideas that are happening, and put it all together into maybe, SDXI2 thought process, because it could be sufficiently different from SDXI1 that we might want to, plan it for later. Okay. So anyway, let me leave it there. We will begin some of this planning with a workshop in New Year.
Sounds good. I'm sorry, I have to drop. So
no, let's all drop. Thank you so much for staying extra.
Okay, great. Thank you so much.
Thanks, everyone. Bye.
Bye.